Icebreakers are built to punch through ice that would destroy any other vessel, but the ice doesn't always move. Under specific conditions, a fully powered icebreaker, engines running, propellers turning, goes completely nowhere. More thrust makes it worse. The solution isn't stronger engines or a thicker hull. It's compressed air, forced through small holes drilled below the waterline. That air forms a bubble layer between the steel and the ice. And that layer changes everything. To understand why introducing air into the hull solves a problem that raw power cannot, you need to see what's actually happening below the surface. Icebreakers are built for one purpose: to move through ice that would stop any other vessel. The hull is reinforced. The bow is shaped to ride up onto the ice surface and crush it under the ship's own weight. The engines are sized to sustain momentum through frozen sea. For a ship moving forward, these systems work. The problem begins the moment the ship stops. In polar pack ice, stopping is not a neutral state. The moment an icebreaker reduces speed or holds position, the surrounding ice closes in. Water displaced during forward motion refreezes almost immediately in sub-zero temperatures. That water fills the gap between the hull and the surrounding ice field. As it freezes, it bonds. The ice does not simply press against the steel, it adheres to it. That distinction matters. Pressure can be countered with force, adhesion cannot. Along the full submerged length of the hull, across hundreds of square meters of surface area, the ice achieves a grip that no engine can simply overpower. This is ice consolidation. It is not mechanical failure. It is the physics of freezing water in direct contact with cold steel. The hull shape that enables ice breaking under forward motion makes this worse when stationary. The wide, sloped bow, built to direct ice downward and outward as the ship advances, presents more contact surface to the surrounding ice field when stopped. The geometry that defines the ship's capability becomes, in certain conditions, the reason it cannot free itself. Extended stops are not edge cases in polar operations. Icebreakers resupply remote research stations, assist trapped vessels, and hold fixed positions during whiteout conditions. Some operational holds extend 8 to 12 hours. During those hours, consolidation pressure builds continuously. There is a threshold beyond which the icebreaker cannot break free independently. Several Soviet-era vessels, fully powered, mechanically intact, required external assistance after consolidation trapped them during routine operational stops. Not because the ships were weak, because the physics of contact had overcome the physics of thrust. That distinction reframed the engineering question entirely. If the failure were structural, the answer would be more steel or higher engine output. But the problem was contact. Ice consolidating against steel in freezing water is an adhesion problem, not a force problem. The solution had to address the contact surface itself, not add resistance against pressure. Engineers working on Soviet polar vessels identified this in the mid-20th century. And the design question shifted from how to make the ship more powerful against consolidated ice to how to prevent the ice from establishing a grip on the hull in the first place. That reframing changed the category of solution under consideration. The answer they developed does not remove the ice. It does not heat the hull. It does not increase engine output. It forces compressed air through small ports drilled directly into the hull below the waterline. What that air layer does to the contact surface between steel and surrounding ice is not immediately obvious, and that is exactly where the engineering logic begins. The system is physically direct in its components. A compressor unit housed within the ship feeds a distribution manifold routed through the hull structure. That manifold connects to a series of ports machined into the hull plating below the waterline, distributed along the sides and bow where ice contact is most intense. When activated, the compressor forces air through the manifold and out through the hull ports into the surrounding water. The result is a continuous layer of air bubbles between the steel and the ice. That layer doesn't push the ice away, it doesn't generate heat. What it does is interrupt direct contact between the hull and the surrounding ice field, and that interruption changes the mechanics of consolidation entirely. Ice adheres to steel because the two surfaces achieve intimate contact. In sub-zero water, the thin film of water between them refreezes across the full contact surface, and creating adhesive bonds distributed across every square centimeter of submerged plating. Those bonds are individually small. Collectively, across a full hull surface, they are enormous. Introducing a bubble layer between the steel and the ice eliminates the conditions that allow those bonds to form. Without direct contact, adhesive refreezing cannot occur. Without adhesive refreezing, consolidation has no mechanism to grip the hull. This is why more thrust doesn't solve the problem, but air does. Thrust acts at a single vector against distributed resistance. The bubble layer addresses that resistance at its source, across the full surface area where it originates. Port geometry and operating pressure are sized to produce consistent, overlapping bubble formation without gaps along the hull. The system performs most effectively at slow speeds and during stationary holds, the exact conditions when consolidation risk is highest. At higher speeds, the ship's forward motion assists ice displacement, and the bubble layer contributes proportionally less. Each port represents a penetration through the hull below the waterline. In extreme cold and pressure conditions, that's a potential failure point. The ports are sized to allow air outflow while maintaining sufficient flow resistance to prevent water ingress under normal operating pressure. A compressor failure results in no air delivery. The ports don't become open inlets. This was non-negotiable for a system intended to operate where external repair is impossible. Performance data confirmed the system worked within a defined range. In first-year sea ice, 1 to 2 meters thick, formed over a single winter season, the bubble layer maintained hull mobility during extended stops. Consolidation did not achieve grip before the air layer broke the adhesive contact. In multi-year pack ice, the conditions change significantly. Ice that has survived multiple freeze-thaw cycles is denser, harder, and capable of exerting substantially higher pressure against a stationary hull. At a certain threshold, the bubble layer reaches its operational boundary. The air continues to flow, but the force required to maintain separation exceeds what friction reduction alone can provide. In first-year seasonal ice, the system performs as designed. In multi-year pack ice, it reaches its limit, and that limit requires a second system operating alongside it. The second system is the healing tank arrangement. Ballast tanks positioned on both sides of the hull allow the ship to roll in controlled lateral cycles by rapidly transferring water between port and starboard. That rolling motion applies shear force along the bond line between the hull and surrounding ice, not forward pressure against the ice mass, but sideways force perpendicular to the adhesive contact. A bond that resists direct forward pressure can often be broken by rotational force applied at an angle to it. In multi-year ice, the two systems operate together. The air layer prevents new adhesive bonds from forming across the submerged hull surface, while the healing motion mechanically breaks bonds that have already developed. Neither is fully adequate alone in the most extreme conditions. Together, they extend the operational envelope significantly. The Lenin-class nuclear icebreakers, which began Arctic operations in 1959, were among the first vessels to integrate both systems in a combined anti-trapping configuration. The engineering reflected Soviet polar design priorities of that period: mechanical directness, field serviceability, and independent redundancy. Each component, compressors, hull ports, healing tanks, could be maintained without affecting the others. Failure in one system didn't cascade. The same logic that governed Soviet military truck heating governed Soviet polar ship design. Independent systems, simple components, serviceable in the field without specialist equipment. The air lubrication principle did not disappear after the Soviet era. As new icebreakers were commissioned by Russia, Finland, Canada, and other nations operating in ice-affected waters, hull air lubrication was incorporated as standard. Contemporary polar vessels carry updated versions. The compressors are quieter, port geometry is refined, distribution is managed by automated pressure control. The operating principle is unchanged. The unexpected legacy came outside polar operations entirely. Naval architects working on commercial vessel efficiency recognized in the 1990s that the bubble layer principle was not ice-specific. A continuous air layer between a hull and water reduces hydrodynamic drag in any water. A container vessel generating a bubble layer along its flat-bottom hull section experiences measurably reduced friction against open ocean water. The fuel savings across a long commercial voyage justify installation costs. Hull air lubrication is now in service on cargo vessels operating in the North Sea, the Baltic, and Trans-Pacific routes with no connection to polar conditions. The system serves no anti-trapping function on a container ship. It exists purely as a fuel efficiency measure. The engineering lineage from Soviet polar problem to global commercial standard was not a planned technology transfer. It was a well-understood physical principle finding new domains where the same logic applied. The icebreaker problem had a specific shape. A hull designed to break ice under forward motion created the conditions for ice to immobilize it when stationary. The solution was not more force. It was less contact. That principle transferred because the underlying physics were never specific to ice. The icebreaker did not need to be stronger. It needed to be harder to hold.